All right. So I got it. The next thing that we're going to do is to get ourselves out of this X and Y kind of deal. And what we're going to be doing is categories. And specifically, the first thing we're going to do is proportions. You remember that back when we were talking about proportions, that we said we're asking people basic yes or no questions, right? Do you own a cat? That kind of thing. So a simple yes or no question, and then the number of successes would be X, and the number of observations would be N, and all that kind of stuff. Okay. So we're working on a similar kind of idea, but there are two different data sets that we want to talk about. The first kind of data set that we're going to have is just a list of proportions. So let's consider something relatively simple here. Derive. Chi-squared 2017. Fit 4. There we go. Okay. So let's say that there's some place that does blood pressure testing, and they have these 4 categories. People that are very low, people that are low, people that are high, people that are very high. And what we're going to say is that we have a certain list of given percentages. So we have multiple categories, and we have to be told there's an expected list of probabilities or list of proportions. So our null hypothesis will be that our population matches the given list of proportions. So we have this given list up here, 10, 30, 40, and 20. And we're saying that's what I think it's going to be. Maybe I can change that, make it a little easier to work. So this is our given set of proportions. Somebody else had to have done some kind of a study to say that this was the thing that's supposed to happen. Okay? We have to be given a list of proportions for this particular kind of thing. Well, then what would be the alternative? The alternative is at least one proportion doesn't match. Or at least one proportion is different from the given set. Now, when we do this process, hopefully you understand, whenever I do a survey, I would expect my numbers to be a little bit different than what somebody told me they were going to be, okay? If somebody tells me it's going to be 10%, it might not be 10%. It might be different. So these numbers really could be anything. I expect them to have some difference, but the question is it a significant difference, or is it just a minor difference? So I want to figure out how much of a difference this is going to be. Now, so this is going to be our always null alternative hypothesis for a particular situation where we're given a list of proportions. And the name of this is called goodness of fit. This is a goodness of fit test. The data that I have, does it fit what I thought it would do? Okay, that's the question that we're asking. So when we do this, we've got null and alternative hypothesis, and it's like, wow, great. What's the next thing that we're supposed to have? A critical value. But the question is, how are we even supposed to do this, okay? And as it turns out, we're not dealing with what we had before with z-scores because there's just too many options here. There's too many different things that we have to work with. If we're comparing 4 different things, which ones do we compare with what? It just gets crazy. So instead of working with the actual percentages, what we're going to do is work on comparing the frequencies or the numbers that are in each category. So we're going to compare frequencies, not percentages. And in order to do that, we're going to be using our chi-squared table. Now you would think maybe that well, first of all, we need to make sure that you understand what's going on. I have observed numbers, 40, 100, 200, and plus 60. This is the number of people in each category. It's a total of 400 people, that's n, okay? You would think maybe we're going to take n minus 1, but we don't. What we're going to do is we're going to take the number of categories minus 1 in order to get our degrees of freedom. So degrees of freedom is k minus 1, where k is the number of categories. Now, so let's do this then for alpha 0.05, right? What's our degrees of freedom going to be then? 3. So degrees of freedom is 3, alpha is 0.05. Emily Grenier, what do you got?
7.815.
7.815. And in these situations, it's a right-tailed test, okay? So it's going to be greater than 7.8. And so far, I think you might be saying, wow, this is great, but we haven't done anything, really. You've just been throwing numbers up here. How do we actually make this happen? Well, this is where it gets interesting. Okay. So then what do we want to do? What we want to do is somehow compare these numbers that we have with what we would expect to get. But we're not comparing percentages, we're comparing frequencies. So I need to get my expected frequencies, E is equal to n times p. You might recognize this as being the average for the binomial distribution. But anyway, this is the expected frequency. But we have to do this for each category. So how's that going to work? Well, n is 400 for my first category, very low. It's 400 times 10%, or 0.10. So that's 400. And then I keep going. Brianna.
How do you know that 0.10 is, what's P?
P is the percentages that are given to us as being the ones for each of those categories. Okay. So thank you. The P comes from our given list. So we have a set of 4 categories. We have a set of 4 proportions that we expect them to be. So we're going to do this 4 different times. We're going to take 10% times 400, 30% times 400, etc. And we're going to have a list of 4 expected frequencies. Question?
So where is like the 400 come from? Like I see that there's 400 for n right there, but like what does that mean? Like
that's the total number of people that we asked our question.
Oh, okay. Sorry.
Okay. So then I would take 400 times 30 instead of. So I get 40, 120, 160. Those are my expected frequencies, and they go by the symbol E. If you want to say E1 is 40, E2 or whatever. But those are the expected frequencies. So, that's our first step in finding our test value. Because our test value looks like this. Chi-squared is the sum of observed minus expected squared divided by expected. And of course, I'll give you this formula. It's on the import formula list. This is the formula that we're going to use in order to compare what we have. We're comparing the frequencies of what we expected compared to the frequencies of what we observed. We're going to put all those numbers into this formula and make that all happen. But what does that look like? Well, as it turns out, our observed numbers were the same for the first one. So that's just 40 minus 40 squared over 40. But we have to keep going with this.
So that's observed minus.
Observed minus expected squared divided by expected. Okay? So now we're doing the second one. This is 100 minus 120 squared over 120. Plus 200 minus 160 squared over 160 plus 60 minus 80 squared over 80. Now this has to work, all right? So you have to be able to put these numbers into your calculator and actually make this happen. The first one, hopefully you can tell, is 0. 40 minus 40 is 0. But I want you to put that second one into your calculator and see if you get the correct answer. 100 minus 20 in parentheses squared divided by 120. What you should come out with is 3.33 repeating. If you do, that's good. That's what we want. And then you'd have to do it again. We won't take the time to do it again. We'll just assume you'd be able to get that the odd answer is 10 and the next answer is 5, and then that would be what you need. Okay? So when we take our test value, we're going to add all those up. And that's going to be a number, turns out to be 18.33. And of course, we'll do another example of this in just a minute, but just to take you through it one time, okay? We have to do this figuring 4 different times. We come up with 4 different numbers, and then the formula says add them all together. We add them all together, we get 18.33. That's our test value. So however many categories we have, that's the number of times we have to do this calculation. The first calculation step is to get the expected frequencies. Then the second calculation step is to find all the chi-squared numbers, use the formula, and then add them all up. So we get the test value. Brianna, question.
What's the weird looking E?
Okay, this thing right here, this is the summation symbol. It means add everything together.
Oh, okay.
So we do this
And then you-
each
okay.
time, and then we add them all.
I'm not sure.
Okay. All right, any other questions about the stuff here? Okay, so that's test value. Amber, what happens next?
Put the test value on the graph.
I put the test value on the graph. What happens when I put the test value on the graph?
You reject the null hypothesis.
I'm going to reject the null hypothesis. This is 18.33, which means I'm going to reject the null hypothesis. Allie, what does that mean? Okay. So now I have enough evidence to prove the alternative. That tells me that something doesn't match. But that's all it tells me. It tells me that there is some of these categories, at least one of them, that doesn't actually match what I thought it was going to be. But it doesn't actually tell me where that difference is, and it doesn't tell me which direction that is. So it's kind of useful in that sense, but it's not really great. Okay. So this is goodness of fit. This is what happens when you do a goodness of fit test. This is what's going to be on your homework. Try to make this happen. Okay. However, on the homework, they also talk about p-values. So we got to talk about p-value. So let's go to our chi-squared table here. And we're going to take a look at the chi-squared table and see what happens. Okay. So I'm looking at this. And if I ask the question, what is the p-value? There's two things I want you to understand about p-value. First thing, and we've talked about this before, but just as a thing right now. P-value is alpha as a variable. So it means the exact same thing as alpha. It's our chance of being wrong, but it's not set ahead of time. We figure it out from the problem, and what we then do in order to understand how the p-value is, it is the area of the tail from the test value. So what I want to consider here is I'm going to look at that test value and I'm going to say, where am I actually when I talk about this test value? Okay. Now, we said we had 3 degrees of freedom, right? Here's 18.33. If I had 7.815, which I'll do a different color, green, I guess. If I had 7.815 here, that would be a tail of 0.05. As I keep going to the right, that area gets smaller. Okay? Could I go out here to 9.3? Yeah, I could. If I go out here to 9.3, that would be my area of 0.025. What if I went out here to 11.345? That's 0.01. That's even smaller. What if I went clear out here, 12.8? That's a really small area, 0.005. But I can still go farther than that, right? This is 18.33. That's way out here. That's really small. But all I really need to know is that my p-value is less than 0.05. All I need to do for this, I don't really need to know what the number is. All I have to know is that my p-value is smaller because I'm out farther. And if my p-value is out smaller than 0.05, I reject the null hypothesis. Small p-value, reject the null hypothesis. So once again, what's going to happen is that you're going to go through the process of doing this stuff. You're going to figure out where your critical value is. You're figuring out where your test value is. If your test value is further out, then your p-value is less than alpha. So on the homework, it's going to say, is the p-value less than alpha? And if it's further to the right, then yes, your p-value is less than alpha. Reject the null hypothesis. Okay, it's the same thing in terms of rejecting by using critical value and test value. But the words p-value are very common out there when people do research. They're trying to say, it's way far out there. P-value is really small. So all you need to know is if it's in the rejection region, the p-value is smaller than alpha. That's all you need to know. All right. The problem with this kind of testing is that it's really not telling us very much about what's going on. If I go back to this, then I look at it and I say, all I know is something doesn't match. Something is significantly different. It's not just a random fluctuation. Some number of people is not what I expected it to be. That's all that this is going to tell me. So again, it's not very helpful, right? We'll come back to that in a minute. But first of all, I want to take another one of these examples and take it all the way through and see if that makes it work. So let's try this. Well, I don't know. That's too much the same as what we had, but maybe it'll work. Let's change these numbers quite a bit. 120, 15, and 5. Yeah. So then we'll change this to be, I'm sorry, I'm working on this. Don't want you to write down these numbers yet. So let's make this 4. Oh, that won't work either. So make this 60, 30. Oh. Well, that'll work. That's a little much, though. That's so much. 40. Yeah, that's probably as good as we're going to get. All right. So this is the situation. We're asking people, what do you take for rain gear? If you know it's going to rain, what do you take with you? We have 4 different answers. An umbrella, a poncho, neither one, I love the rain, or something else. You know, I drive my car, I don't ever walk in the rain or something. Okay? Now, what we have are these observed numbers. Okay? And I think I'm just going to take these out so they don't distract you too much. All right. So we're given these percentages. And we observe these categories. These are when we actually ask people, these are the numbers we got, but somebody said this is what we expect them. So what I want you to go through is to see if you can make this happen. All right? Find those expected values and figure out what the chi-squared .
You just want the frequency right now?
Well, I'd like to do the whole thing, actually. Get the frequencies and do all the chi-squareds too.
Okay.
All right, so maybe check with your neighbor, see what your neighbor's got going on. If it looks like what you've got. So these are what you should have for your expected values: 150, 25, 50, and 25. Okay. Now let's see if you can get your correct chi-squared numbers from that.
You just keep going along.
Is n times p always going to be equal in each respective column?
Yeah. The n, the total number of people multiplied by each of the given percentages. That's how you get your expected.
So can we skip that step? I mean, are we always gonna have the expected column?
You're always going to have the expected column because you have to do that in order to do that. In order to put in these values of E, you have to know what they are.
Right.
So you have to have, if you have 4 of these, you gotta have 4 of these.
I mean, the step where you multiply N times P.
Okay, what number goes right here? I don't know. 250 times 0.6 gives me that number.
Yeah,
What number goes here?
that's what I'm saying. Do we have to do that multiplying it every time?
Yes. Because this is not given to you,
Oh, I see what you're saying.
okay?
Yeah.
This would be
Okay.
given to you, but this would not.
I already wrote it down.
Aha, see, there we go.
Okay,
All right.
thank you.
Now, what about the chi-squared values? Good question. What about the chi-square values? What about those chi-square values? There they are. 2.67, 1, 0, and 9 adds up to be 12.67. Okay. So any questions about where those numbers come from or how to get them? Again, hopefully it's clear that if your observed and your expected are the same, then that's chi-squared of 0, right? So what we're actually measuring is how different is this set of numbers from what we expected it to be. According to this, it comes out to be chi-squared of 12.67. That's our test value. So once again, if we have similar thing, we would go out here and make our consideration. Again, degrees of freedom, k minus 1, so in this case it's 3. That's going to put us in the same place. We're going to reject the null hypothesis. We're going to say some category is different. There's some situation where the category is different. Question, Emily.
So what is this gonna look like in like a homework question? Because it's not, I'm sure they're not gonna like give us like, is it gonna be like a word problem where we make this?
I'll show you.
reference?
I will show you what it's going to look like. That's a great question. We go back to our resources page,
That's what you're doing right now.
assignments, publisher site. Kill that one. Here.
Oh, chi-squared. It's right here. So.
Chi-squared. Eric, chi-squared.
Chi-squared.
Thank you. All right.
Chi is something different.
It is. So this is what a homework problem will look like. Here is on-time performance by the airline. This is the percent of time that airplanes arrive. 70.8% of the time they're on time, et cetera, et cetera. These are the 4 categories. These are the given percentages. But they made record of 200 flights, and these are the observed numbers: 147, 25, 15, etc. So then we take these are the observed numbers, we would write them in our observed list. And then for the expected, we'd be taking 70.8% times 200. Because n is 200, and then we multiply that 200 times each one of these percentages. And that would give us our expected list. Okay. Now, identifying the claim, for whatever reason, the textbook thinks that's wonderful. I don't. But when we say, do these results differ from the government statistics? That's the only thing we're able to prove. We're only able to prove that it's different. So in this situation, the claim is that they are different. So that would be the alternative. Okay, the second one. All right, so that's what it's going to look like, very much like the concept of what I have for you here. Okay, so this isn't good enough for us, however, because this doesn't really tell you what's happening. It doesn't tell you if one of these categories is actually higher than one of the other ones, or lower, or anything. So this is something which is not in the textbook, but we'll talk about it during class. Hopefully it'll make some sense to you here, okay? So we'll talk about this every day from now until the end. So here we are. What happens when I have my observed values is that will give me an observed probability, which is p hat. So now I have a p hat, which is not the same as what I was given. I was given that it would be 60%, but it actually was observed to be different. It was 52%. I thought this would be 10%, but it's not. It's 12%. So, okay. So I have all of these p hat values, and based upon those p hat values, I come up with confidence intervals. These are my confidence intervals. What's the purpose of a confidence interval?
Yeah.
No. What's the purpose of the confidence interval?
Measure something about a population.
It's to measure something about a population. What are we measuring here? Are we measuring mean, proportion, or standard deviation? Proportion. These are confidence intervals for the proportion. So if we ask the question, what is the actual value of the population proportion? It's between 44% and 60%. It's between 7% and 17%. It's between 14% and 27%. And this proportion is between 10% and 22%. Okay. Do these match up with my given set of proportion? That's the question that I want to answer. Do I have any of these confidence intervals which is different from what I expected it to be? Most people don't understand this, so give yourself a chance, okay, to think about it and not freak. All right, that happens every once in a while, so don't freak. But right here, what we're looking at is a list of confidence intervals. Confidence intervals are telling me the real population numbers. These are my population numbers. They're in here somewhere. Are they different from what I expected them to be? That's my comparison. I am not comparing these to p hat. P hat is always in the middle of these. So that's not the issue. The issue is what I expected it to be. Is this different than what I expected it to be?
The given column.
From the given column. Are those given numbers different from what I have in my confidence interval?
You have two of them right on the line.
Okay. This one looks like it would be below my expected. Because it's pretty much all of these are below 60%. So that's below what I expected. And this one is above my expected. So what I would say is this number came out to be 52%, and that gives me this confidence interval, which is lower than what I expected. People don't use umbrellas as much as I expect them to. So this one is lower. Yeah,
Okay, but like 60% is literally on the given, how is that below 60? The same
it's
number.
on the border, that's close enough for us. Okay, if it's close enough, we're gonna say yeah. It's like, are you over the speed limit? You're at 55.
Sure.
Okay. When something's on the border, if we say, well, let's say, how much money do you have in your pocket? Somewhere between $44 and $60. You're gonna go out and buy something that's $60. You're probably low. 44 to 60. So we're not talking in terms of knowing everything exactly here. We're mostly below 60. So that when we look at this, by looking at these confidence intervals, I can specifically say which proportion is not what I expected it to be, and which direction is that difference. Umbrella proportion is lower than I expected it to be. Other proportion is higher than I expected. These other two, I can't really tell. Because they could be lower, they could be higher than I expected, I don't know for sure. But these two, I can say more or less, are different from what I expected them to be. Like I said, this is not easy. Something you're not going to see in your textbook, but we're going to talk about it a lot.
What did you find p hat again?
P hat is x divided by n. So that would be 130 divided by 250. P hat are all the observed proportions for my observed frequencies. All right, so we're going to get rid of this because we have another big topic to handle. Let's get rid of this for now. Okay. So now we're going to talk about a very different thing. Instead of talking about a list of proportions, we're going to be talking about a table, which is going to have rows and columns. So let me see if I can get this thing set up to make it work. Okay, so what we're going to do is we're going to measure what sport people like. Football, basketball, or something else. And we're going to ask a bunch of business students and a bunch of nursing students. Now, when we do this, notice that we have categories, like I said before, categories, and we're putting people into the categories. We're just asking them a question. But we have two questions. Are you in business or nursing? And then, what sport do you like? Football, basketball, or other? So we're putting people into categories, but this is a two sets of questions. So when we do that, we're just putting them in there and we're seeing what the numbers are. Now, as you look at this thing, do I have a lot of people that like football? Yeah, it's higher than the others, but it's not a ton higher, right? Do I have more nursing students than business students? Yes. I have 600 nursing students and I have 200 business students. So it would seem reasonable that if I look at the football lovers, I would have 3 times the nursing students as I have business students. But that's not how it worked. I have 100 business football fans. I only have 200 nursing football fans. I would think if everything was just kind of equal, that I would have 3 times as many, but I don't. Compare that to the basketball fans. I do have 3 times as many here compared to there. So it seems like being a basketball fan is not affected by being either a business or a nursing student because the proportions are staying the same. So what do we call this thing? Well, what are we looking for? H0 says that the categories do not affect the proportions. H1 would be categories do affect the proportions. If I have 3 times the number of students, do I get 3 times as many of the fans? Sometimes I do, sometimes I don't. So is there a relationship here? Is there some kind of an effect as to how many people like a thing, which is related to what program they're in? Now we can't do cause and effect here. We can't say, if you're in nursing, that changes your sport preference necessarily. We could even say, if you like a certain sport, does that make you go into nursing? We can't say that either, okay? But all we can say is that they're somehow related to each other. These have names, these things. This is called independence. And this is called dependence. Are the categories independent or are they dependent? And so the name of this thing is called a test of independence. Well, guess what? We're still going to be doing a comparison of frequencies. We're going to be using the same equation with the observed and the expected values. Some other things are going to be different, but at least that part is the same. Okay. We have our null and alternative hypotheses. The next thing is a critical value. Degrees of freedom is the number of rows minus 1 multiplied by the number of columns minus 1. And you have to be aware of what we're talking about here. We're not talking about these total numbers. These numbers on the bottom and on the right, those are the column totals and the row totals. We're just talking about these numbers right here. So there are 3 rows, minus 1, and 2 columns. 1, 2 times 1 is 2. There are 2 degrees of freedom. So what's our critical value for 2 degrees of freedom in alpha 0.05? 5 point what?
991.
5.991. Okay, so far. Now, how do we get our expected values? Each expected value is the row total multiplied by the column total, all over the table total. I'm not going to try to explain the theory behind it, but we're just going to go with it here. Say, this is what we're going to do. Yes. So let's think about what that would look like. The first row is 300, the first column is 200, and the overall table is 800. So I'm going to take 300 times 200 divided by 800. What do I get? $75. So what I need is another table, actually. And I'm going to put a 75 in the first row and the first column. That's my expected value for the first row and the first column. Let's try the first row and the second column. What will that be? The first row is 300. The second column is 600. And it's divided by 800. What was that? $225. Nikki is on a mission to get these numbers. Nikki, if you haven't looked around, nobody else was pushing their buttons. So there you go. You get that, 225. Okay. How many times do we have to go through this process? A total of 6. There are 6 numbers in the table. We need 6 expected values. So we would have to go through and find the rest of these as well. In the interest of time, I'll put them out here. Each part of the table has its own row and its own column. We take the row total for that cell times the column number for that cell divided by the overall total. That tells us what expected value to put in that cell. Brianna.
So then the next one would be like 240 times 200 divided by 800.
That's correct.
Okay.
And so on. These numbers, which we have in front of us here, these expected numbers are independents. They would be the numbers if everything was just according to the correct proportions based on the numbers of people in the different parts. So as I look at my expected values, you'll notice that the second column is always 3 times the first one because we had 3 times as many nursing students, and so on. All of the proportions would then be independent. which would mean it doesn't matter whether you're in business or nursing, your preference for the sport would be the same as everybody else's, whether you're in business or in nursing. That's what independence means. However, that's not the numbers that we have. The numbers that we observed are different from these expected values. So what do we got to do? That, chi-squared. So we're going to take each of these expected numbers and each of these observed numbers and go through and do chi-squared for each other. So the first one would be 100 minus 75 squared divided by 75. And hopefully you'll believe me when I say that chi-squared number is 8.33. And then we would keep going. How many times would we have to do this? 6 times. We would have 6 different chi-squared numbers. Now, turns out that middle row right there is 0 because it turned out just to have the right proportions. So that's 0. But then we're going to add them all up. And come out with a value of 23.93. So what does that tell me? I'm in the rejection region. I reject the null hypothesis. I prove the alternative. The categories do affect the proportions. If somebody's in nursing, their preferences are not the same as the people in business. But that's all it tells me. It tells me something is different. It doesn't tell me what. However, we're not going to go through a confidence interval thing here because it would be very complicated. We would have to do 1, 2, 3, 4, 5, 6, 7, probably 7 different comparisons. And as we do more and more comparisons, our chance of being wrong goes up and up and up. So it's just not worth our time right now to try and make that happen. But right now, what we are able to say is something is different between the business students and the nursing students in terms of their sport preference. This is how a lot of, if you want to say, survey results are figured out. They'll look at how people respond to all these different survey questions, and then they'll say, okay, do people with higher incomes have a higher rate of supporting military than others? How would I know that? I would have to put the people into categories and figure out where the differences are. So this is how that works. Now, as it turns out, they will do the same p-value thing on the homework as we talked about earlier. So if they say 23.93 is way out here, that means the p-value is less than 0.05. That's the same thing as saying it's in the rejection rate. The p-value is less because that tail is smaller. That's what that is. All right, that's enough. Only one more topic after this.